Chapter 6, Part 3, Designating Chiral Centers. We use the R&S system to designate chiral centers. The R&S system uses the same priority system that we saw with the EC system. We use the R&S system to designate chiral centers in order to differentiate between different stereoisomers of a molecule. The rules are that you first assign each group attached to the chiral carbon a priority based on atomic number. This is the Kahn-Ingold pre-log system that we learned for EZ. And then you rotate the molecule so that the lowest priority is in the back. Typically, this is a hydrogen in a lot of the examples that we work. And then you determine whether the path from the first to the second to the third priority is rotating clockwise, which gives the designation R from the Latin rectus, or counterclockwise, which is S from the Latin sinister. R also matches up with to the right, and S matches up with to the left, which is actually where the word sinister here is coming from. So let's work these two examples and see if we can figure this out. So the first thing you do is you need to identify that chiral center. And then you assign each group that is attached to the chiral carbon a priority based on atomic number. So we have a hydrogen, an oxygen, and we have two carbons. So we'll have to use the Kahn-Ingold pre-log system to work out those two carbons. But the hydrogen is going to automatically be our lowest priority, so we're going to give it the number 1. The oxygen is more important than the carbons, so we're going to give that the number 1. And then we have to compare our two carbons here. It's pretty obvious that the methyl group is going to be smaller than the ethyl group, but remember with the Kahn-Ingold pre-log system, you work out one level at a time. So this is comparing carbon to carbon, and then you go out to the next level. So we have carbon, hydrogen, hydrogen versus hydrogen, hydrogen, hydrogen. And that's what ends up making the ethyl group the higher priority. So this is going to be group number 2, and this is group number 3. So now the rule says to rotate the lowest priority to the back. So what that means is you want to position your molecule so that the lowest priority item is on a dashed wedge, meaning it's pointing away from you. You can kind of picture this like a steering wheel. The low priority is going to be the steering shaft that holds the steering wheel. And then you are connecting your priorities 1 to 2 to 3 with a circle and seeing if your steering wheel is turning to the right or to the left. So if we take the steering wheel from 1 to 2 to 3, then our bus or a car or whatever you're driving would be going to the left. This is counterclockwise. This gets the designation S. Now let's do the other one. We've already figured out these priorities, so I'm going to scribble those on real fast. The oxygen is the high priority, and then the ethyl, and then the methyl, and then the hydrogen is our low priority. It's already positioned to the back, so we don't have to do anything extra there. And now we connect our priorities 1 to 2 to 3. I think it's obvious that this is the opposite of the molecule we just did, and this is going to be R, but let's prove it. So we're connecting 1 to 2 to 3. This, if we were using the steering wheel analogy, you would be turning your car to the right because you're turning your wheel clockwise. So this gets the designation R. When you are doing the Kahn-Ingold pre-log system, remember that groups containing double or triple bonds are assigned priorities as if both atoms are duplicated or triplicated. So the way this works out is you have to use fake atoms essentially. So if we were trying to analyze this bond here, the 4 different things that the carbon atom is attached to is this bond, and then it's attached to the Y, but it has 2 bonds to Y. So we give it Y star. It's a fake Y, it's a placeholder. And then similarly, the atom Y has 2 bonds. One of them is to carbon, which is already represented here, and then the other one is also to carbon. So we use C star in order to indicate that. And when we have things in triplicate, you just have to draw several more stars. So here are some practice problems that include those multiple bonds. So let's work the first one. We have this chlorine sitting on this carbon, and let's go ahead and fill in our hydrogen because we need it in order to do this. Hydrogen is going to be our low priority. The chlorine is obviously going to be our high priority. So now we have to decide, we have carbon and carbon here, but then when we get out to the next level, the carbon on the left is attached to a carbon and two hydrogens. The carbon on the right is attached to a carbon and a hydrogen, and then we also have to fill in that C star. So carbon C star hydrogen is more important than carbon hydrogen hydrogen. So our alkene is going to have the higher priority. So let me switch my priority numbers so they're easier to see. This is going to be the next priority, and then number 3. So then we connect these 1 to 2 to 3. This is rotating clockwise. This gets the designation R. So if this makes sense to you, go ahead and pause and try to work out the last 2 problems. Note that the last one has 2 chiral centers that you would have to designate. If this does not make sense yet, go ahead and don't push pause and just follow along. So we're going to start here at this carbon. This is the only one that any stereochemistry is being indicated on. And we need to fill in our hydrogen. So we automatically have some pretty easy things that we can fill out. We have 4 on our hydrogen. The oxygen is our high priority. And then we are comparing carbon to carbon. We can't make a decision at that point, so we go out to the next level. This carbon has a carbon, a hydrogen, and a C star. The other carbon has the oxygen, a carbon, and an O star. So this one is going to be the higher priority. So our next priority is here and then here. The low priority group is already pointing to the back. All of these examples have that, so we don't have to think too hard yet. So let's go ahead and connect these. We're going 1 to 2 to 3. This is clockwise again, so this is also an R isomer. So this next one is going to get 2 designations. We have to come up with one for each of the chiral carbons. The first thing I would do when you see multiple stereocenters is just be sure that you are actually looking at chiral carbons. I kind of made that assumption here. But this one is chiral. We have a hydrogen, we have a methyl, and then we have all this and bromine. So it's definitely chiral. And this one over here, it's pretty clear that there's a lack of symmetry. We have the tetrabutyl group, tert-butyl group, and then we have this entire chunk. We have the hydroxyl, and of course we have our hydrogen. So both of these are chiral. So let's start with giving out our easy priorities. 4 to 1. Now, I should make you go through all the work, but I think it's pretty clear that the methyl is not going to beat this. So let's go ahead and give ourselves a little bit of a break. Methyl is going to be the next lowest priority, and then the second highest priority is going to be the other side. So let's go ahead and do this designation. We're going to connect 1 to 2 to 3. This one is also R. Now I'm actually going to erase the work that I just did here because I want to be able to do the other side clearly. So I'm going to erase that. So this stereocenter has an R designation. Now we have to do our next one. So the obvious ones we can mark down, 1 and 4. Next one, we have carbon versus carbon. We have to go out to the next level. Carbon, carbon, carbon versus carbon, hydrogen, and C star. The fact that this carbon has a hydrogen at all is kind of a pretty quick indicator that it's going to be the lower priority. So the tert-butyl group is going to be the next highest, and then we have 3. And again, our low priority group is already pointing to the back, so we don't have to do anything special. We're going to connect 1 to 2 to 3. This is going counterclockwise. So this is going to be an S stereocenter. So now we're going to combine some of this information. It says identify the molecules below as diastereomers, enantiomers, identical, or constitutional isomers. So there's a couple things that you should do here. First, I would go ahead and number it like you were naming it and figure out if it has all the same stuff attached in the same order. This will help you rule out whether or not these are constitutional isomers or if they're actually stereoisomers or potentially identical. And then if they are not constitutional isomers, meaning their atoms are not rearranged in different ways, then I would figure out the designation at each of these carbons and then match them up and see if the designations are the same or if they're indicative of being diastereomers or enantiomers. So go ahead and pause and at least come up with those designations. Okay, I'm going to walk you through this in case you need it. If you don't need a walkthrough, feel free to skip ahead a couple minutes. So we have this carbon here. The bromine is going to be number 1. Our hydrogen is pointing to the back. And that's going to be our low priority. And then we have, this should be your second priority, and then your third. 1, 2, 3. That's rotating to the right. This one is R. Oh, also, the initial work that would need to be done to see if they're constitutional isomers, they are not. They have the same longest chain, 1, 2, 3, 4, 5, 6, and the connectivity of the alcohol and the bromine are the same. So, and then on the next one, we actually have something kind of tricky. The hydrogen is coming forward. So there are 2 ways that you can address this. You can either attempt to rotate the molecule or rotate the bonds in order to give yourself the hydrogen in the back, or you can do my cheater's method here, which is to come up with your designation. So this is 1 to 2 to 3. This looks like an R stereocenter. But since my hydrogen is in the front, I'm actually looking at this backwards. The analogy that I tend to use for this is, I already mentioned that this is kind of like the steering wheel. It's the driving or the steering shaft. So if we are all riding on a bus together and I turn my wheel clockwise, the whole bus is going to go to the right. But what if you're standing on the street and you're looking at the bus? So at the drive shaft or the steering column? I don't work on cars. Steering column, I think is actually the right term, is pointing towards you. Then you're going to observe the bus turning to your left, not to your right. So if you're on the wrong side of the molecule, you're going to observe the opposite thing. So what we're observing right now is a turn to the right, which means it's actually going to the left. So I always just come up with my designation and then I flip-flop it if my low priority group is coming towards me. So this molecule is R on the bromine and S on the alcohol. So let's do the same thing for the other molecule. I'm going to put out our priorities. We have bromine. The hydrogen is actually going away from us this time. That's going to be 4. And then 3 and 2. So this one goes 1 to 2 to 3. That's to the right. So this is an R. And then on our last one, the hydrogen is coming out at us again. So whatever determination we come up with, we're just going to flip-flop it. So this is 1, 4, 2, 3. So this looks like 1, 2, 3. It looks like it's going to the left. So to us, standing on the street watching this bus, we see it going to the left, but it's actually turning to the right. So we have an RS isomer versus an RR isomer. That makes these 2 molecules diastereomers because they're not a mirror image of each other. If they were a mirror image, then we would have seen, if this is RS, this one would be SR because the chiral centers would be flip-flopped, but only one of them got flip-flopped. So that is the definition of diastereomers. This next slide is discussing absolute and relative configurations. This is kind of a conceptual idea that I just want to throw out there as we are starting to get into some reactions where we're about to see how the reaction can affect the relative configuration of a molecule. So absolute configuration is a term for R&S designation. You can look at a molecule, figure out its designation, and say that is the R configuration of that molecule. That is the R isomer. Relative configuration is when you have two molecules that share certain groups in common, and those groups are arranged in the same way. You would say that they have the same relative configuration. So this is an example here. We have these atoms X and Y, and they overlap each other if we were to superpose these molecules. We would also see that A ends up on top of A, B ends up on top of B, and C ends up on top of C. So these have the same relative configuration. This may not be the same absolute configuration though, because depending on the molecular weights of X and Y, it's possible that X is the lowest priority atom on this molecule, but Y is the high priority atom. And that would change the absolute configurations so that they may actually have opposite configurations in these circumstances, even though they have the same relative configuration. So a more definitive example that shows this is, you'll notice this entire bottom part overlaps, but what's different is the fluorine and the iodine. Now, fluorine is a much lower priority than iodine. If we were to dish out the priorities on this molecule, bromine would be the high priority, hydrogen would be the low priority, and then between oxygen and fluorine, fluorine is higher than oxygen. If you remember, we have that row of the periodic table going this way, and then we have our halogens, Cl, Br, and I below. I wish I'd left a little more space for that when I was trying to show my plan here. So when we do the priorities on our next molecule, the iodine is going to be the highest priority, followed by bromine, followed by oxygen, and then hydrogen. So these two are going to have different absolute configurations. For our first molecule, we're going counterclockwise, so that would be S. For our second molecule, we're going clockwise, so that would be R. So even though they do have the same relative configuration and the chemistry is happening in one specific place without affecting the other pieces, their absolute configurations ended up different. So this will be kind of important in chapter 7. Now we're going to see how we add in R and S designations into the names of compounds. So one thing you might want to go ahead and do is pause and figure out the chiral configurations of everything. So give R and S to every chiral carbon. I'm going to do that, but I'm going to talk through them. I'm just going to talk through them a little more quickly than I have been. So looking at these two chiral carbons, I have 1, 2, 3, and then my hydrogen is going back, that's 4. So this is going to be R. I'm going to erase that because it's in my way. And then I have a hydrogen coming out, 1, 4, 2, 3. That's going to be S. So I have those figured out. I'm going to erase all this stuff so that the nomenclature becomes easier and just scribble that in, R, S. Okay, going to do the same for the next ones. 1, 2, 3, and my hydrogen is already pointing back. This one's R. And then this next one, ooh, this one's a little bit trickier. So we have carbon versus carbon versus carbon, but this one has an oxygen on it. So I think that's going to end up being our high priority, second and third. 1 to 2 to 3. Counterclockwise, that's going to be S. So I'm going to plug that in there. Okay, this last one has 3 chiral centers, so that's a fun choice that I made when I made these examples. Okay, my low priority is coming towards us, so whatever we decide, we're going to have to flip-flop. So this looks like R, but it's actually S. So that looks like a sigma, so let's try that again. S. Okay. Next one, I have high priority, low priority, and then bromine is higher priority than chlorine. So 1 to 2 to 3, that's S. And I'm going to keep my designation as is because my low priority is going away from us. And then last one, I have bromine. My hydrogen is coming towards us, so whatever we decide, I'm going to flip-flop. 2, 3. It looks like S, so I'm going to call it R. Okay, so we now have all of our designations. So from here, we can jump to the naming. So we're going to follow just all the same rules that we already know. Pick a side to start numbering from. 1, 2, 3, 4. I don't think there's any sort of priority system for putting R or S, but I numbered from the left. So this would be a 2,3-dibromobutane is the bulk of the name. And then to indicate which specific stereoisomer this is, because there are multiple, we're going to call this 2R3S. Put a little dash there. So we're just listing our locants and our designations. Okay, next one. This is a derivative of, well, not a derivative, but it is an isomer of 2-methyl-cyclohexanol. And I'm going to add 1R2S. You could also call this cis, but remember there could be 2 different cis 2-methyl-cyclohexanols that are actually enantiomers of each other. 1R2S is how you are specific about which enantiomer it is. Okay, last one. We need to decide which side we're going to start numbering from. It's kind of the same numbers no matter which side I start from, but bromine comes first alphabetically, so we're going to give bromine the priority. 1, 2, 3, 4, 5. So this is going to be a long one. 2 bromo. Oops, not 3 chloro, 4 chloro. 4 chloro, 3 pentanol. 2 bromo, 4 chloro, 3 pentanol. And then we have to shove all those letters and numbers in the beginning. We have 2R, 3S, 4S. And that is how you include your designations in your nomenclature.